I'd like to teach you about inelastic collisions. Now, in contrast to elastic collisions, which I spoke about in the previous video, kinetic energy is lost from the system as a result of an inelastic collision. Now, it turns out that most collisions are actually inelastic. Take a look at this PHET simulation. We're going to do some calculations involving both momentum and kinetic energy. We're going to predict that momentum is conserved because momentum is conserved during all collisions for a defined system. We're also now going to predict that our kinetic energy will be greater than the final kinetic energy. Please recall that we're summing the momenta and also summing the kinetic energies both before and after the collision. So let's get to it with this simulation. Let's first calculate the sum of the initial kinetic energies. So we have for the light blue colored ball, we've put in both the speed of the ball and the mass of the ball. And we did the same for the magenta colored ball. Notice I've included signage for the leftward velocity of the magenta colored ball. However, recall that kinetic energy will give us a positive value anyways because we're going to square the negative 0.5 meters per second. We end up getting an initial kinetic energy for this two-object system to be 0.44 joules. Now let's see if kinetic energy was conserved in this collision. We would predict, however, that it was not. And of course, I'm teaching you about inelastic collisions in which kinetic energy is lost from the system. Doing the same for the kinetic energies after the collision, we get that the kinetic energy is 0.12 joules. So indeed, a total of 0.32 joules was lost from the system to the environment in the form of heat, sound, and deformation of particles. Now let's go ahead and calculate the initial momentum for the system. We're plugging in the values for the mass and velocity, and this time we do need to pay attention to our signage as momentum is a vector quantity. So when we plug in these values, we get that the initial momentum for this two-object system is negative 0.25 kilograms times meters per second. Recall that this is the same as saying a Newton second. So I'm interchanging my units because I want my students to be aware of both. They are both perfectly acceptable. Let's sum the momenta for the two-object system after the collision, paying attention to the signage, noting that the light blue colored ball is now moving in the left direction and the magenta colored ball is now moving in the right direction. We get that the final momentum for this system is also negative 0.25 kilograms times meters per second. So momentum is indeed conserved for this two-object system. Now let's go ahead and look at the individual momentum for the objects in this system. Now we're going to look at calculating the time of impact. So you're given the fact that the force of ball 1 onto ball 2 was 200 newtons. And you're being asked to calculate the time of impact. We're going to use the go-to equation right here, and we're going to look at the individual momentum. Remember that even though momentum for the system is conserved, individual momenta for objects within our system is not. So let's go ahead and calculate the change in momentum for one of these objects in our system. In other words, let's calculate the impulse, because if we can calculate the impulse, then we can set that equal to the force multiplied by the duration of time that force was applied. That will enable us to solve for time. So looking at the magenta colored ball and taking its final momentum and subtracting from that its initial momentum, we can find that the impulse exerted onto the magenta colored ball is 0.84 kilograms times meters per second. We can now acknowledge that that value is indeed the impulse, which means we can set that equal to force multiplied by time. We can now divide both sides of this expression by the force of 200 newtons to isolate for time. Solving, we get 0.0042 seconds or 4.2 milliseconds for that time of impact. Now take a look at this simulation in which the objects stick together after they collide. This is a special type of inelastic collision called a perfectly inelastic collision, and sometimes also referred to as a completely inelastic collision. The two objects will stick together after they collide. This type of collision results in the greatest loss of kinetic energy from the system to the environment. Also notice that the composite object after the collision has the same velocity. This is very important to consider when solving problems involving an inelastic collision. Let's go ahead and do one now. Let's look at our initial momentum for the two object system. Let's consider signage as momentum is a vector quantity. We have the magenta ball initially moving to the left, and we have the light blue colored ball initially moving to the right. We can calculate the initial momentum for the system to be negative 0.25 kilograms times meters per second. Now let's do the same after the two objects collide. And you're going to see mathematically we're doing something very different than we've done thus far in this unit. We're going to look at their final momentum. However, we're going to sum the mass because we now have a two-object composite system. In other words, they are stuck together. So our total mass for these two objects is going to be 2 kilograms. Also notice they share a final velocity, and that final velocity is negative 0.13 meters per second. Now we predict, is momentum conserved for this collision? And the answer is, of course it is, because momentum is always conserved for an isolated system. So we get the exact same answer before and after the collision. Now, in this video, I've taught you about inelastic collisions, and I've also taught you about a special type of inelastic collision called a perfectly inelastic collision. You now understand that, of course, momentum is conserved for the system. However, kinetic energy is lost in these collisions from the system to the environment. And I'll see you guys in class.